might lead to reignition, all sorts of other interesting dynamics. And that fluctuation in the combustion process will then introduce a change in pressure, an acoustic change, which that pressure can then couple back and influence the hydrodynamics all over again. We've got a closed feedback loop, and bad dynamics can ensue. So really what I want to focus on this work, or on this talk is on the hydrodynamic aspects of combustion instability, and then to add to that, specifically in swirling flows. And so we're going to go through two extremes in this talk. We're going to talk first about the nice, easy to understand stuff, which is laminar flows, and then kind of what can we learn about laminar flows, or what can we learn from laminar flows that we can then apply in more complicated turbulent type flow fields, which are really what's practical. So this, what I'm about to show you here is a visualization of a non-reacting swirling flow in a pipe. So we've just got quasi-flow with a rotating pipe. The pipe was just started right when I started the video. And what we see is that as the pipe's rotation accelerates, the viscous stress at the wall is causing the flow in the interior to swirl. We get this nice, eventually, this nice solid body rotation type flow. And that spontaneously induces this vortex breakdown flow feature in the field, which is just appearing now. So what we noticed here is that after, basically as the swirl reached some critical level, this stagnation point appeared and grew. This is an axisymmetric feature, and the helical type motions you're seeing here are due to misalignment in the die injection and stuff. This is nominally axisymmetric. There's no sort of helical instability modes happening here. However, helical instability modes are a really common feature in swirling flows. And still, this is sort of a pseudo-laminar case, at least at the dump plane here. This is a non-swirling jet here, which we're going to kind of look at as the swirl number increases. So if you look at the kind of the limit of zero swirl, we have this nice axisymmetric jet, axisymmetric vortex rings, before eventually we get a decay into turbulence. As we increase swirl number, we see a kind of progressive effect of the effective swirl on this jet. And so first what we notice is that there's kind of a misalignment of these vortex rings. Eventually those misaligned rings transition to fully helical rings. And then beyond that, we also see this emergence of the vortex breakdown phenomenon again, which is not only the same feature we saw in the last flow, which was a swirling pipe flow. This is a totally different type of flow, but we still see the same kind of canonical feature, which we see in all sorts of swirling flows, whether they be jet-type flows like this, or annular jet-type flows, which we've seen in some of the previous talks for combustion systems, and so on and so forth. Important things to notice here, or the important thing to notice here is that this is all at a fixed Reynolds number, so really the only thing that is changing here is just the amount of azimuthal velocity per axial velocity. It's kind of how you can think of the swirl number. So we can think of similar effects if we look at the effect of the Reynolds number. We basically transition, if we start at the limit of a really strongly viscous case with a relatively high swirl number here, we not only have columnar flow. So basically we have a slender vortex which is propagating, or which is basically the flow continues to rotate. Viscous forces prevent that vortex breakdown bubble from appearing. As we start to increase Reynolds number, we see sort of a divergence from this columnar flow state, where at first it's just sort of a minor deflection of the flow around the center line. And then at a Reynolds number of 100, in this case, this is a flow-specific number. But in this case, we see kind of the emergence of this axisymmetric vortex breakdown. And then beyond that even, we see helical or spiraling type instabilities which appear at even larger Reynolds numbers. And so we kind of get the idea of this transition, of separate transitions between sort of a columnar state, which might be what our vortex generator or our swirler generates. And then there's sort of an evolution beyond that where we get this sort of axisymmetric breakdown feature. And then beyond that, typically in the wake, at least at lower Reynolds numbers, typically in the wake of that bubble, we'll start to generate these helical or spiraling instabilities. And so we get a nice kind of convenient picture in non-reacting flows, which is a bit of foreshadowing, of the dynamics which are at play here. Basically we have a competition between vortex stretching and dissipation, which determines what the vortex dynamics that we see when we look at the flow are. There was a really nice paper by Maliga which kind of summarized what I just tried to kind of quickly show in the last few slides. This is a plot of swirl number and Reynolds number for a flow called a Grabowski vortex, which is a really common kind of canonical flow in swirling flow literature. Basically, the lightly shaded region here is any flow with a stagnation point, and the darkly shadowed region is any flow with that is unstable to a helical mode. And so basically we see that there's, for most of these swirl numbers, we basically have axisymmetric breakdown feature, and then beyond that, the generation of a helical instability, which either has a periodicity of 1, 2, 3, or 4, typically 1 or 2, depending on the swirl number. This is a visualization of what a flow like this would look like if we were at this point here. So a swirl number of 1 and a Reynolds number of 1 for a Grabowski type vortex. We have just a fixed inflow condition, no boundaries anywhere else other than the inflow really. And we look at the flow kind of comes in this columnar state and quickly forms this stagnation region. This is a steady solution of the Navier-Stokes equations. If we look at the dynamic, the kind of the linear modes of this steady solution, basically we can linearize about this and look at what happens to any kind of helical disturbance that we'd superpose on this. We can look at their eigenvalues, and since the imaginary part of these eigenvalues is negative, we know that none of these disturbances that are helical would be amplified in this flow. So what we would say is that this flow is stable to helical disturbances. So in essence, and this agrees with what we see here, in essence, this point here has a stagnation point, but you would not expect to see any type of helical vortex shedding or anything like that on here. However, if we go to the reacting case, first off, let me show, there's a jump here as we go to the reacting case. I'm really using just a simple chemistry model, and I don't want to get too much into the dynamics of this, or the nitty-gritty of the simulation. But suffice to say, when we introduce reactions, we see a huge increase in the size of the bubble, and that's due to our flame, gas expansion due to the flame. And we also see some kind of broader changes in the wake region. And it might be easier to see this if I show you what the flow looks like as a whole. So here, what I'm showing you is a steady solution to Navier-Stokes. And then I linearize about that steady solution, and I say, is it stable to m equals 1 or m equals 2 or arbitrary helical disturbance modes? And it turns out that for m equals 1, there is an eigenmode which does have a growth rate. And so basically this flow quickly saturates to a limit cycle with an azimuthal periodicity of 1. And so if we look at what that limit cycle looks like, basically we see this nice oscillation of these kind of helical vortex shedding. This line here basically is a contour of reaction rate. So basically we're looking at sort of a pseudo, like a flame, basically. And what we see is at the back of the bubble here, we start to see this kind of precession of the vortex bubble. And at really low Reynolds numbers like this is basically what the precessing vortex core is. At much higher Reynolds numbers, basically this instability will climb around this bubble and begin to move the bubble more as a whole. But at the really low Reynolds numbers like this, it's really controlled just in the back here. And so what we saw here was a case where the flame destabilized the flow. This was the same flow parameters, we just basically added heat release to this flow and allowed it to go to this vortex breakdown bubble anchored flame type solution. And the flow became unstable to helical disturbances. But that is in no way a general result. It's actually a very complicated process, which is actually pretty poorly understood. There's a lot of factors that really contribute to stabilizing and destabilizing these types of flow fields. And simply saying I want to throw a flame on there, is that going to make me more or less stable, is not a question that's very easy to answer. And it's something I'm trying to answer, but I can't give you any really nice general answers yet, other than it's complicated and you have to do a pretty sizable analysis to really understand it. But basically we go from having this nice competition between stretching and dissipation to produce these flow dynamics, to having all these different vortex dynamics in addition to flame dynamics and thermodynamics, which kind of all come together to produce what we see when I'm interested in fluid dynamics, and so what I'm saying is my output here essentially is what are the flow dynamics as I look at this part of the combustion instability problem. So that was a way to that was kind of the first chapter of this talk, which is how can we understand the laminar flow case, and now let's think about how we can apply what we may or may not have just learned there, to the turbulent flow case. And so a really useful way to look at turbulent flows, at least turbulent flows with kind of large-scale structures in them, is called the triple decomposition. And basically what we do here is we break down any flow variable, which I'm calling phi here. It could be a velocity, a pressure, whatever you want. And basically whatever this complicated variable in space and time is, we decompose it into a time average, a coherent part, which in this case we could just say this is a single Fourier mode. It could be whatever you define it to be. We're doing this without any approximation. We're basically just splitting this up into 3 components. And so I just want to kind of illustrate what this expansion is doing. So we can think of what I showed first, this kind of laminar type oscillation, as being the sum of a steady solution, which takes us to some point in phase space, and is kind of the steady solution we saw in Navier-Stokes, plus some vector which oscillates harmonically and gives us this kind of limit cycle motion. And so basically we're thinking about this laminar solution as having a steady part, or a time average part, and a coherent part without any type of incoherent or stochastic or turbulent noise, whatever you want to call it. And then we can go to another extreme where we have sort of whatever you want to call ideal turbulence, where we just have a probabilistic solution where there is absolutely no coherent structures, and we just kind of get a mean part of phase space, which is kind of just in the center of some kind of hairy ball like this, and then sort of a probability distribution of where we might expect to find ourselves in phase space about that kind of mean solution. So these are kind of two extremes, but between the extremes, which is where we typically are, we look at turbulent swirling jets, is that we have sort of a mix of these kind of coherent structures, which are the larger ones, in addition to kind of turbulent structures, which are typically the smaller ones. And so in that case, we look at a mean part, which kind of takes us to the middle of phase space. But in this case, it's interesting to note that even though this is what something like a RAND simulation might generate as a final result, it's really of no interest to us because the system spends almost no time there. If you think of these red points as observations, at no point do we really observe the flow in this state. And then a coherent part, which we can think about the flow as being the sum of these two components, because on average it spends a pretty significant amount of time on that kind of limit cycle oscillation. And then in addition to that, we've also got some sort of probability distribution about that limit cycle. And so this is kind of an important distinction between just sort of a pure type of time average perspective on this problem and sort of a coherent structures type perspective on this problem. How am I doing on time? Okay. So the question is, can we predict this via hydrodynamic stability analysis, which is what I've been trying to describe here. So I showed earlier a model, and now I want to talk a little bit about some results that we can, or a way we can apply this kind of modeling to real types of systems. So this is some experimental, I'm using some experimental data that was not taken by me. Tim's had many great PhD students go through, who many of you are still on this facility and are familiar with this facility, in room 119, I think. I spent very little time actually in the combustion lab, if it's not obvious. But basically we have premixed reactants coming through. In this case we're just running through one nozzle, methane air lean flame. We also have the potential to force the flame. If we look at a close-up right near the dump plane here, we basically have a plane where we do simultaneous high-speed OH, PLIF, and PIV, both in a kind of longitudinal plane and in lateral slices. So we can, this kind of slice here is this one, kind of if we're looking down this exhaust window here. And then in addition to those kind of measurements, we also can provide forcing, and what we can use this to do is to force the system to have coherent structures at a certain frequency. So we can kind of get these two types of cases where we force it symmetrically, and what this tends to do is produce kind of ring-like oscillations, symmetric with respect to the center line. And we can also do velocity antinode forcing, where we basically force the flow to slosh back and forth. And we, of course, prescribe the frequency with our forcing, in addition to this kind of very basic shape of forcing. So if we look at results from the measured flow fields from this, basically what I'm plotting on the left here is instantaneous images of vorticity in this longitudinal plane. Then we're looking at the time average, and now this is a static frame of the coherent part, and this is a coherent part as a function of phase. And so we see this nice kind of cascade of coherent structures which are exist in the out-of-phase forcing and the in-phase forcing case. And this case is basically just showing you that there's very little energy in the non-force case. How much time do I have?
30 seconds.
30 seconds, okay. Well, let me run through these results really quick. So we've got, what I'm showing here are measured amplitudes. This is just of an axisymmetric mode and just of a helical mode, and then the sum of all these modes. And then these are predicted modes from linear stability analysis. And just to quickly get through, I'll try to answer any more questions in the question section. Basically what we see here is that very near in the kind of first half of this plane, we see not only linear growth of disturbances, which we can see both in terms of the predicted modal amplitudes and the measured total amplitude in the near field. And then if we look down at the phase velocities, we see that the phase velocities of the disturbances kind of synchronize and allow themselves to nonlinearly interact in a way which no longer causes them to grow in the way that would be predicted by linear stability analysis, but rather by a nonlinear process. So I will close with a couple of cool videos that show some of the other work that's going on in Tim's group, and take any questions.
Chris, are Reynolds number effects on the vortex breakdown process, is that geometry specific, or could that be applied across a variety of different geometries?
Geometry is a really important part of the picture. I didn't want to give the idea that it wasn't, but the Reynolds number typically has a consistent effect on a particular geometry, but that may not be the same effect across different geometries.
Do you know how much in terms of, I don't know, energy maybe the completely random part contributes to your decomposition?
I can quantify that in the case of the flows I looked at. It varies a lot depending on how strong, basically it depends on how strong your coherent structures are. Okay. If you think of a combustor undergoing combustion instability, that coherent structure is probably a very significant fraction of the total energy in the flow. Whereas in a case where it's kind of more stably operating, and you kind of think of more broadband type turbulence, then the stochastic part would be a more significant fraction of the flow energy. Does that answer your question?
Yes. Do you have a number on that? Like ballpark?
I would say that about 80% of the energy is distributed across all frequencies, whereas maybe 20% might be concentrated at these flows at least, where I didn't impose forcing, but where Travis imposed forcing on these flow fields, these types of flows had about 20% of their energy in the 390 Hz component. And then 80% is distributed across all of the frequencies. So a significant amount more in that one frequency component.
How do harmonics of the coherent structure affect the stability?
That's actually that's a really good question. So the harmonics tend to generate, basically if you look at an n=1 type oscillation, you're going to have n=2 type harmonics. Or if you look at it in a frequency perspective, you're going to have 2 omega type harmonics. And so those basically they have no effect on the linear stability of the flow, as long as we take a time average, because that's all included in whatever we measured in the first place. However, they do have a really strong effect on the nonlinear dynamics. So once we're talking about finite amplitude disturbance modes that are able to interact, it really does have a huge effect on how they do interact. That is how they interact.
So something that you talked about kind of early on when you were first talking about adding heat release to the flow as opposed to a non-reacting flow. So I might be able to pull that slide up. I was curious how you would characterize the relationship, if there is one, between the precessing vortex core and helical modes.
So the helical mode is a disturbance which rides on this solution here. So basically, if you took these streamlines and subtracted these streamlines, you would get the helical oscillation. Actually, I think that it might be a better thing if we think about it here. Basically, we have a solution, this part of the solution here, this is what describes our helical modes. This
Okay,
is
so
this solution here is just a axisymmetric steady vortex breakdown feature.
Yeah, so I was just wondering, would you always say that if there's a precessing vortex core, once it starts to kind of spin around, that there's always some type of like helical vortex mode?
I mean, if
So it's like
there's something that's not axisymmetric, then there's going to be, just in the way we've defined the flow field, if we're talking about an axisymmetric type environment, if it's not axisymmetric, it's definitely helical in terms of the decomposition.
Yeah, I guess what I was trying to ask is like, do you have these kind of like discrete helical vortex cores like spinning around anytime you have a precessing vortex core? Like, is it right to think of those as the same thing?
So it's complicated because this is a nonlinear thing, so we can't think about just like taking this as the sum of a vortex core and a disturbance which is off of the vortex core necessarily, because they're linked. Once we have a limit cycle, if we looked at a real flow, they're definitely linked. And so I guess, I don't know if this answers your question or not, but the vortex breakdown is a typically unsteady solution of these equations, upon which there rides these shear layer instabilities, which can have large amplitudes either in the wake of the bubble, in which case you see sort of a really small precession, or it can climb up and around the bubble and start to really drive these really large scale precessions of the vortex core. But anything that's not axisymmetric is helical mode, but in the way it's defined here.
Okay. Unfortunately, that's all the time that we have for questions. Let's thank our speakers.